Do you like the music before class? Yeah, I read an article and it said that really helps students to sort of make the transition from not class to class. I'll try to remember to do it. If you have any requests for songs, as long as it's not like real violent, like heavy metal or whatever. Hey, Luana. Let's see. Oh, let's do some questions. All right, so no, the exam isn't the day we come back. It's the day after we come back. So we get back on Thursday and we have class then, and then the next Tuesday we have an exam. All right. That's on your syllabus. It's the 24th, I think, if I'm not mistaken. Is that right? 24th? All right. Consider what happens when you push both the pen, like a push pen, and the blunt end of a pen, like a writing pen, against your skin with the same force. What will determine whether your skin will be punctured? Pressure on your skin, the net applied force in your skin, both pressure and the net applied force are equivalent, or neither the pressure nor the net applied force are relevant here. So which of these values, the pressure or the force, or both, or neither, are relevant whether your skin will be punctured? I want you to think about this. So let's say that you have a pen, this is a blunt pen, and you apply it to your arm with, just sort of, I'm pushing on it a little bit. What would happen if I took a push pen and pushed on it with the same amount of force? What would happen? Would it puncture my skin? Likely, right? So I'm using the same force for the writing pen. I'm not going to do it with a push pen, but if I pushed on it the same amount with a push pen, it would go into my arm and, it would hurt. So what's relevant there? Is it the force, the pressure, both, or neither? All right, I'm going to stop at 145. 145. Ooh, yeah, C is a good answer. That's not really what I was looking for. This question isn't very well worded. What's the answer I'm looking for? A, the pressure on your skin. Because the pressure actually does include the net applied force, right? Because pressure is force over unit area. So I'm going to say that A is the right answer here, but I'm going to concede to your C as well. But that's an okay answer, but not exactly what I'm looking for. You follow what I'm saying? Probably not the best question. Wouldn't see one like that on your test, but you do need to know what the definition of pressure is. Right, you're walking out on a frozen lake and you begin to hear the ice cracking beneath you. I'm sure y'all done this before. Like walk out over the frozen bayou. What is your best strategy for getting off the ice safely? Come up and down. Try to leap to the bank. Shuffle your feet or lie down flat. I'm going to stop at 50 seconds. 50. All right. What you want to do here is you want to decrease the amount of pressure that you're applying to the ice. And remember, pressure is force over area. So one thing that I can do is just decrease the amount of force that I apply. But, my weight is what it is, right? So I can't really decrease the amount of force. So the other thing then is I could do something to the area that I'm applying to the ice. And so what can I do to decrease, or would I decrease or increase the amount of area? To decrease. A what? Increase. only if I make my area bigger, then I have less pressure applied to the ice. So what am I going to do here? E or E? E. I'll do E. If I lie down, that increases my area, which decreases the pressure. Remember, our pressure is force over area. So if I increase my area, that decreases my pressure. When swimming near the bottom of a pool, you let out, like you blow out a small bubble of air. As the bubble rises toward the surface, what happens to its diameter? Okay, very good. Y'all doing a good job. I'm going to stop at, say, 35. I think you probably know this answer intuitively. There are a couple of things at play, though. C is the right answer. First of all, what's happening as the bubble goes up? What's happening to the pressure? It's decreasing, right? Because pressure is dependent upon the height or the depth in the fluid. So our pressure is decreasing. And so you probably intuitively know, well, if my pressure decreases, my volume gets bigger, right? But that's also stated in something that we learned recently. What was that? Some law that we did? The ideal gas law, remember? EV is equal to nRT. So that's demonstrated here. So I have PV equals nRT. Now this is the amount of gas. So in the bubble, the amount of gas is what it is. So it's constant. And the temperature of the gas is also constant. And so if my pressure goes down, then my volume has to go up. Similarly, like we said with our lungs. Like if with our lungs, we're changing the volume, and then that changes the pressure. Here we have a very similar thing where we're changing the pressure, and then that changes the volume. I'm going to sort of rewrite this one just a little bit. I don't like this last figure. It's a little misleading. So let's say that I have three objects, three things, and they all have the same base, right? So this area is all the same. One is just a cylinder, two is like a trapezoid, and then three is like a really big bowl, right? What does which container has the greatest force acting on its base? Which container has the greatest force acting on its base? They all have the same height. I've drawn three a little bit incorrectly. They're all filled to the top, and they all have the same surface area on their base. Which of these has the greatest total force acting on its base? Obviously, they have different amounts of fluid in them. One has the least, two has the next, and three has the most. Which has the greater force acting on its base? All right, I'm going to stop at 118. Oh, no, not C. D is the right answer here. All three are equal. This goes back to our pressure. So if I think about the pressure at the same point in all three of these containers, the pressure right here, the pressure right here, and the pressure right there, they're all going to experience the same pressure at that point. As a result, you'll also have the same pressure acting on the surface area of this base. Now they'd have different amounts of fluid, so along the sides of this container they'll have different forces acting. But along the surface area of the base you'll have the same pressure. And since they all have the same area, then they'll also feel the same force. when you drink liquid through a straw, which of the items listed below is responsible for that to work? That is to drink liquid through a straw. Water pressure, gravity, inertia, atmospheric pressure are the mass of the liquid. Feel free to ask your neighbor, y'all doing pretty good. I'm going to stop at 45 seconds. 45. You're so close to having a perfect score. Ask your neighbor what they put. All right, I'm going to stop at 1 minute. 1 minute. All right, D is the right answer. Remember, we talked about this, that when you drink liquid through the straw, it's that pressure from the atmosphere that's pushing the liquid down and then up into the straw and into your mouth. And all you're doing really is just causing a slight difference in pressure. So you're causing a slight vacuum inside of your mouth that causes the atmospheric pressure to work, to push that liquid up into your mouth. I think that's good enough for a joke, don't you think? You want to hear one? This is pretty good. Did you hear? Well, it's a little sad actually, but did you hear about the guy that he was in an accident? The entire left side of his body was cut off. Like he lost his left arm and his left leg. Did you hear about that guy? He's all right now. Y'all heard that one? Yeah. Okay. All right. You put a straw into a glass of water, place your finger over the top so no air can get in or out, and then lift the straw. You find that the straw retains some liquid right before you fling it at the friend right next to you. Right, y'all do that? We do that a lot. How does the air pressure P in the upper part compare to the atmospheric pressure PA? Let me see. You can't see the bottom, but down here there's an arrow that points up that says PA. So my PA is actually here, and I have another pressure here. How does this pressure compare to the atmospheric pressure? Is it greater than the atmospheric pressure, equal to the atmospheric pressure, or less than the atmospheric pressure? Not many of you have put A, right? But A is not the right answer. Let me explain why A isn't the right answer, and then maybe that'll help you sway you into the right answer. A is not the right answer because if this pressure was greater than the atmospheric pressure, what would happen? It would force it out violently, right? It would push it out violently. It would be like spitting the water out of the straw. Right? So A is not the right answer. So which is the right answer? Y'all ask your neighbors. More of you have the wrong answer than the right answer. You also want to think about that you have a certain force that's at work here due to the weight of this fluid. There's a certain force at work here due to the weight of the fluid. And somehow you have to overcome that force. No, you're talking to the wrong people. Ask somebody else. No. All right. We're stopping at 2:30. I'm sorry. It's backfiring on me. Okay. We're sort of back where we left off. So, yeah, the answer here is C. That the pressure is actually less than the pressure PA. Let me see what the explanation is. Yeah, that's not a very good explanation, but it's less than that pressure PA because I have this pressure pushing up, and then I have this pressure here. But I have to have a differential in pressure in order to support the weight of this fluid, right? Now, if they were equal, if these two pressures are equal, then the fluid would just fall out. It wouldn't be forced out violently like if this was bigger, but it would just fall out because there wouldn't be a differential in pressure in order to support this weight. All right, so these two pressures are different, actually, by a certain amount. By what amount are they different? If I were to calculate what that amount is different, we did this. Like for it's like a barometer, right? Well, it's sort of like a barometer. It's different by that rho GH. Remember, pressure is rho GH. Those two pressures are different by that amount. The density times the acceleration due to gravity, which is 10, times h, which is the height of that column. Okay, just one or two more. In a mercury barometer, at atmospheric pressure, the height of the column is 760 millimeters. If another mercury barometer is used that has a tube of larger diameter, how high will the column of mercury be in this case? So I have one barometer that's like this, and it goes up to 760. And then I have another barometer that's like this, and it's asking how high will the fluid go up in this barometer if this one goes up to 760. Will it go up to a height greater than 760, less than 760, or equal to 760 in this new barometer? So two barometers. One's really skinny, like they usually are, but then you say, well, I want to make a big old fat barometer. And how high then will the mercury go up into this tube? Will it go up a distance greater than 760, equal to 760, or something less? It's not necessarily electronic. All right, y'all put a pretty reasonable answer, but let me show you something. All right, we know that pressure due to this barometer is equal to P naught, that's the pressure inside the barometer, plus rho times G times H. And with a barometer, we know this is a special case, so that P naught is equal to 0. So our pressure, which is the same here as it is here, is equal to the density times the acceleration due to gravity times the height of the column. So my pressure, which is 1 atmosphere if I'm at sea level, is equal to the density of the mercury, which is the same in both barometers, times G, which of course is the same, times H. And now I want to know how high will this column of mercury be for this big old barometer. All right, folks, I'm going to stop at 225. Okay. Okay, good. More of you. That's some sways there at the end. These two are going to be the same because look, this relationship has nothing to do with the diameter of the barometer or the cross-sectional area of the barometer. It only has to do with the height. In fact, if you remember back when I showed you that little derivation, or sort of that thought that we had for what is the pressure due to a fluid of a certain depth, we said we imagine this little box, and on top of that little box there's set a big column of liquid. You remember this? Maybe? And then we said that the weight of this fluid, or rather the pressure, is equal to the weight of the fluid over the area, and the weight of the fluid was mass times G over the area, and then that was rho Vg over area, and then the area canceled out. So it turns out that the area of that imaginary column of fluid that we imagine doesn't have anything to do with the pressure. It's only the height of that column. And that's borne out in this expression, that we don't have an area of our tube here, or volume or any of that, it's just the height. That's a good thing, because then we don't have to worry about getting all of our barometers the same. That we can make a tube of any diameter, and it's still going to work the same way. Now, why would you want to make a little skinny barometer as opposed to a big round barometer?
Less mercury.
Well, that's mercury, yeah, and also, yeah. So you want to use as little mercury as possible. That's the main reason. But also, if you have a really big barometer, you have to be darn certain that you have a good vacuum here, right? And it's more difficult because this is going to be supporting a greater weight of mercury up into that chamber. So it's easier to build one with a thin diameter, a small diameter. Oh yeah. So thermometers often use mercury or alcohol in a thin glass tube, but barometers never use alcohol. Why is this? Mercury is less flammable. It's true. Mercury's color is easier to see, and less toxic. It's more dense, or it's cheaper than alcohol. Very good. Doing a good job. I'm going to stop at 55, okay? If you're not certain, ask one of your neighbors. Excellent. D is the right answer. It's more dense, so it's like that Veritasium video that we watched, the straw. Right? If he was sucking up mercury instead, then the height of the straw that he would be using would be much smaller, like maybe 760 millimeters. Whereas if you use, say, alcohol or water or something about that density, then you have to go to 10 meters high to measure out an atmosphere of pressure, and that's just not real practical. We'll get to this. We're going to do fluid flow today. We might come back to these today. Let's see, where did we leave off? We were looking at pressure and solids and stress and strain. We're going to come back to stress and strain. We'll talk about it in relation to our bones and what have you, and sort of the breaking limits of our bones. But right now we're going to shift gears into fluids in motion. Yeah, so fluids in motion. It's kind of a fun thing. I like this topic. Fluids in motion. We call this fluid dynamics. The study of this is called fluid dynamics. It can be very complicated, but we're going to take some sort of simplifying looks at it, which are not unrealistic. In fact, a lot of fluid flow is what we call ideal fluid flow. So we're going to look at ideal fluid flow in particular. Remember that fluids do include all things that flow. That's what the word means. Now let's do a quick question. So which of these is a fluid? Water, air, jello, or wood? Water, air, jello, or wood? Which of these is a fluid? Is it A, one only, B, 1 and 2, C, 1, 2, and 3, or is it D, 4, or E, all of these? Which of these is a fluid? 1, water, 2, air, 3, jello, 4, wood. Is it A, just water, B, water and air, C, water, air, and jello, D, wood, or E, all of those? Which of these is a fluid? Stop at 35, 35. Yeah, so fluids do include all things, all liquids and gases. We talked about that before. Although we'll see in this chapter that some things might not look like fluids, but they actually do flow, and that's sort of a sticky place to be. All right, let's look at characteristics of fluid flow. You sort of need to be just knowledgeable about these characteristics and then also be able to identify when fluids are ideal or not ideal. I'll show you what I mean by that in just a second. So first thing is that fluid flow, this is characteristics of fluid flow. They can either be steady or unsteady. That means that the velocity at a particular point does not change. So if a fluid has a steady fluid flow, that means the velocity at a point does not change. All right, so in a steady fluid flow, I have a pipe and it has fluid flowing through it. Then the velocity at a particular point, say at this point, is always going to be the same. Now it might be different at different points in the pipe or whatever, but always at that point, the fluid flow will always be the same. So this is one of our properties, steady, of an ideal fluid or ideal fluid flow. And so, but this occurs often. Like if you have just water flowing through a pipe, then that's often an ideal fluid flow. It has a steady flow where it's always at the same velocity. And even in the human bodies, a lot of cases it's not steady, but in some places it is steady, or we can assume that it's steady. The second thing is rotational or irrotational. Right, and an ideal fluid flow will be which of these? It will rotate or not rotate? Huh? No, it doesn't rotate. So if we're talking about an ideal fluid flow, it's going to be irrotational. So that means the fluid does not rotate. Now when I say rotate, I mean, you know, it's not going to rotate like a tornado or whatever. Right, like a nice example of rotational fluid flow, you pull the plug on your bathtub, right, and the water starts to rotate as it goes down the drain. That's rotational, and that's not a property of an ideal fluid flow. The third thing is viscous, I think. Yeah, viscous or non-viscous. The non-viscous here is our property of ideal fluid flow, and it just means that this viscosity, there's no viscosity. This viscosity arises because of friction between the molecules, that they literally stick together or they rub up against one another, and it causes the fluid to flow very slowly. So what are some examples of viscous fluids? Okay, yeah, blood. Often it depends, like there are levels of viscosity, and we'll talk about how that interacts with flow, but yeah, it can be viscous, huh? Molasses and like pancake syrup and stuff like that. I have an example here of a very viscous fluid. This is the pitch dropic. Okay, so viscous or non-viscous. For an ideal fluid, we're looking at non-viscous. So in a practical terms, a non-viscous fluid would be something like water, for example, which is has a very low viscosity. And then one more thing, actually two more things, and that is compressible or incompressible. We've already talked about this a little bit. This is number 4. We've already talked about this, so I'm going to ask you a question. Liquids are blank, gases are blank. And your answers here are either going to be compressible, compressible, B, compressible, incompressible. I'm going to abbreviate it, okay? Compressible, incompressible. C is incompressible, compressible. Or is it D, incompressible, incompressible? So liquids are either compressible or incompressible, and gases are either compressible or incompressible. Which is it? C is compressible, I is incompressible. So liquids and gases are collectively known as fluids, but how are they different, or how are they the same in their compressibility? Doing a good job. Just a few more seconds. I'll stop at 35. Very good. C is the right answer. Liquids are incompressible. That is, if I apply pressure to a liquid, it doesn't change its volume. Right? It increases pressure inside the fluid, but it doesn't change its volume. And if I do the same for a gas, then it does change its volume. And we saw that with the ideal gas law, that PV equals nRT, that our pressure and our volume are inversely related. So if I increase my pressure, I decrease my volume. All right. For an ideal fluid flow, which of these do you think is relevant for ideal fluid flow? Does our ideal fluid, should it be compressible or incompressible? Huh? Can you try again? Incompressible. Good job, Emily. Yeah, so for our ideal fluid flow, we're looking at incompressible. So that's just going to limit us to very low viscosity liquids when we talk about ideal fluid flow, that are moving at a steady speed and that are not rotating. And one more thing is that it's laminar or turbulent. So number 5 is it laminar or turbulent? When I say laminar, it means this. There's a definition in your book similar to this. But the fluid flows in parallel layers. I'll draw a picture to show you what I mean. With no interaction between the layers. So as a result of this, like if you have a pipe, so you have a pipe, you have a fluid flowing through it, you can imagine that it's split into different layers. Let's see if I can change the shape of this. You can imagine different layers going through. So I have one layer of fluid and then another layer of fluid, and the two don't interact, basically. So what you can have in this is that you can have a layer of fluid here flowing, and then have a layer of fluid flowing up here, and they can have different speeds. Right? So for example, the speed in the middle will be more or less than the speed along the sides, do you think? Will it flow faster in the middle or on the sides? In the middle, it's going to flow faster. On the sides, you deal with the fluid sort of sticking to the sides of the pipe. So laminar is when it flows in these parallel layers. Now, if you get turbulent flow, then all these layers sort of get mixed up together. Right? And we'll talk about turbulence, like in the heart, for example, where these fluids all get jumbled up together. You don't get this nice laminar fluid flow flowing in layers. So in your arteries and veins, you do often get this laminar flow. So we'll talk about that later when we get to the second part of this chapter. And for ideal fluid flow, we're talking about laminar flow. Turbulent flow can be very complicated mathematically, but there are people that simulate it. All right, let's look at flow rate. You had some questions about flow rate on your quiz, which I'll return in just a little bit. By the way, y'all did get your grades for the quiz. I put them on Moodle. I didn't update your clicker points. I'll update that after our next, after the exam coming up soon. All right, so when we talk about flow rate, we're going to use the variable Q for flow rate, and we're going to define this flow rate as a rate of volume over time. So what volume of fluid passes a point in a given amount of time. And so since volume has units of cubic meters in the SI system, and time has units of seconds, then our SI unit for Q will be meters cubed per second. This can also be, we can also express our Q in terms of the cross-sectional area. So if I have, a pipe or whatever, and it has a cross-sectional area A, and it has a certain flow of fluid V, A is in meters squared, V is in meters per second. We can also express this Q in terms of the velocity and the area. So it would be equal to the area times the velocity. And you can just look at the units on this and you'll see that they're the same. So I have meters squared times meters per second, and that'll give us meters cubed per second, which is the same here. This comes about because with the velocity we're talking about a length, right? The length of the pipe, and then we're multiplying that length of the pipe times the area of the pipe, and that is the volume. Length times area is the volume. So these two are equivalent, the volume per unit time, or the cross-sectional area times the velocity of the pipe. And one thing about incompressible fluids that falls out of them being incompressible is that this flow rate has to be the same at all points in the fluid. If you have a fluid that's incompressible, if you have a liquid flowing through a pipe, then the flow rate has to be the same at all points in that system. This is true for our circulatory system as well, or at least we could make some slight assumptions that the flow rate is always the same. Now your speeds might change along the way, and we'll see that later, that when your vessels get smaller or bigger, then that V will be different, but the flow rate must always be the same. So for an incompressible fluid, Q must always remain constant. And it's a simple argument. Like let's imagine that we have a pipe, and I have a Q down at this end. I measure my flow rate to be, I don't know, 10 cubic meters per second. And then down at this end, I measure my flow rate to be Q equals to 9 cubic meters per second. All right, what's the problem with that? If I'm talking about an incompressible fluid, one that doesn't change volume, okay, so it has to keep the same amount of volume. With this scenario, what's the problem if I'm going from 10 to 9 cubic meters per second? Why is that problematic? What does it imply about the system? Open. It's open, so it means that I'm losing something somewhere. So it means that between this point and this point, I'm losing a cubic meter per second of fluid. and that's why my flow rate is smaller here. Or on the other hand, if I measure this to be 11, it would mean that I'm gaining fluid from somewhere. So if I have a closed system, this flow rate has to always be the same. And that's true for our body as well. I mean, our body isn't truly it's not truly a closed system, but it basically is. So this flow rate has to remain the same. All right. Now, out of that comes the continuity equation. So the continuity equation is just going to say that Q at one point is going to equal Q at another point. It just says that Q at one point is equal to Q at another point. And more commonly, it's written like this: that the area at one region times the velocity. This isn't the volume. This is the velocity. Is equal to A2 V2. By the way, we're going to be dealing with volume and velocity a lot, so I'm going to write a little thought bubble up here, sort of just to let you know how I differentiate between the two. When I write volume, I write a capital V, and I try to make it very straight like this. So when I write it, I'll write it like this, volume. And when I write velocity, I'll write it as a lowercase v with sort of that script. Okay? Hopefully that'll help. We're going to encounter volume very soon, and we've already encountered it some, actually. All right, so this is the continuity equation. It just says that the product of this area and velocity have to remain the same. This is important for you. Let's imagine that I have a pipe or a system that's big and then it gets smaller. This has a certain area. We'll call this A1. And it flows through here with a certain speed, V1. And down here, I have a certain area, A2, which is obviously smaller. And down here, I have the speed, V2. I want to ask you a question. Is V2 A bigger than V1, B smaller than V1, or C equal to V1? We're assuming this is an ideal fluid. It's laminar, it's irrotational, it's incompressible, it's what's else? It's non-viscous basically, and it's steady. So which of these is true? Is V2, the velocity in the second portion of the pipe, is it greater, less, or equal to V1? How does V2 compare with V1 in light of this continuity equation and in light of being an ideal fluid flowing through this system? All right, doing pretty well. Just a few more seconds. I'm going to stop at 55. 55. Okay, good. V2 is bigger than V1. That comes about from this continuity equation. Our flow rate has to always be the same. A1 V1 is equal to A2 V2. So look at how the quantities are related to one another. When I go from A1 to A2, I find a drop in A2. All right, but I know this value, A1 times V1, remains constant. So if A2 drops, if A2 drops, then that means that V2 has to increase.
It's ideal and it's steady. It says that the velocity at a point is not changing.
That's a great question.
So
right. Yeah, thank you. So when you say steady, it's the velocity at a particular point. So for example, at this point, the velocity is always going to be V1. But at this point, the velocity is always going to be V2.
So it can be different.
Right. At different points, you can have different velocities. Thank you for pointing that out. But at different points, you can have different velocities. But in an ideal fluid, at the same point, you'll always have the same velocity. That's a great point. Okay. Where do you see this? Where do you use the continuity equation? ever have a garden hose? What do you do with a garden hose? You put your thumb over it, right, to squirt people, right, or whatever you do with your garden hose. And when you put your thumb over it, you decrease the area of the hose, or when you put a kink in it or whatever you do with it, you decrease the area, and that increases the velocity. We'll talk about it too in the circulatory system because we find that the area decreases quite a lot in our circulatory system as we go from our heart out to the capillaries, and so that's going to affect the velocity too. Before you say, well, oh, but blood doesn't flow fast in capillaries, right? It actually flows quite slowly. We'll talk about the sort of the total area and how that affects the system. Is that what y'all are about to say? No. Okay. Let's see. This continuity equation. Let's just do a quick little problem, okay? You could see a problem like this on your test. Simple. Let's just say I have a pipe. I have an area. The area of this pipe, let's say A1, is equal to 4 square meters. And here I have a velocity equal to 2 meters per second. And over here, I have an area equal to 2 square meters. And I just want to know what is the velocity here, V2. All right, I'm going to give you some options. Go ahead and work it out. Is it 2, 4, 6, or 8 meters per second? 2, 4, 6, or 8 meters per second? All right, I'm going to stop at 110. 110, just guess if you don't know or ask your neighbor. Okay, B is the right answer. You can think about this. You could work it out, right? You could say A1 V1 is equal to A2 V2. All right, that would be 4 times 2 is equal to my area A2 times V2. That's 8 equals 2V. V has to be 4, right? I would go through this. I would divide by 2 on both sides. And so I would find then that V equals 4 meters per second. So D is the right answer. Excuse me. You're going to encounter some basic mathematical problems like that on the test, something similar to this. I would pretty much bet on it. But you could also just look at it and say, well, the area is down by a factor of 2. That means my velocity has to be up by a factor of 2. My velocity was 2 meters per second here, so it has to be twice that here, or 4 meters per second. All right? All right. Okay, we sort of already talked about this, but what do you think happens to the fluid flow as the viscosity increases? Do you think that the fluid flow, that rate Q, do you think it goes up, goes down, or remains the same? As your viscosity increases, what happens to your fluid flow? You know the answer to this. What happens? Right, the fluid flows at a slower rate, right? If I pour pancake syrup out of a bottle, it pours more slowly than if I were to pour water out of a bottle. And that's because it's more viscous. That viscosity is dependent upon a number of things. Mostly it's just the makeup of the material, but but sometimes it's also like the temperature, for example, like the supercool helium, the temperature got really, really low, and that made the viscosity go to 0. So I think we've already covered that. So let's go ahead and I'm going to introduce the Poiseuille equation. You had some questions on the reading quiz related to this equation, the Poiseuille. Poiseuille. Am I saying that right? I think I'm saying Poiseuille. Can y'all say it? Poiseuille. Yeah, it looks like Poiseuille, but it's Poiseuille. I looked it up on the internet, Caitlin. This is it's French. It's Poiseuille. Yeah, so it looks like this: Poiseuille. The Poiseuille equation. So you did have a question on your reading quiz about this, and so you'll see similar questions. You know, how is the fluid flow rate related to different things? And Q, I think on the quiz it was like the length of the tube or something. It looks like this. Poiseuille equation says that the fluid flow rate is pi r to the 4th times delta P divided by 8 eta L. That's the Greek letter eta L. Alright. We're just really going to be focused on the relationships between these variables. So if you do something to one variable, what happens to the flow rate, for example? Like if I increase the radius of the tube in which it's flowing, keeping everything else the same, then the flow rate will increase, right? Where r is the radius. So let me just sort of define what these variables are first. R is the radius of the tube, or the vessel, whatever it is. Delta P is the difference in pressure. Right. In order to have fluid flow, you have to have a change in pressure between two different points. This eta, this sort of script N looking thing, it's a Greek letter. And this is eta. This is a measure of a material's viscosity. Spelling that right is within this. Yeah. And then L is the length of the tube. I'm going to give you all of your equations that you'll need for the test. So, like, for example, you'll have this on the side. On your reading quiz, you won't have it, but for your test, you'll have this and various other equation continuity equations, the Pascal's principle that F over A is constant, F over A equals F over A. So you'll have all those equations, but like for example, on your reading quiz, you had a question. It was something like, if the length of the tube goes up, what happens to the flow rate? And so you would look at this and I'd say, well, the length of the tube here is L. If L increases, what's going to happen to my flow rate, keeping everything else constant? It's going to decrease. So if I have a longer tube, it's going to be hard. It'll be the flow rate will decrease. Now, if my flow rate is the same, like if I increase this, that means I have to do something to one of these others. Now, to keep the same flow rate through a longer tube, normally you would increase your pressure, and then that would keep the same flow rate. All right, so like for example, if you're trying to blow water through a long hose, you have to blow harder on a long hose than you do on a short hose, right? When I was a kid, we used to siphon gas a lot out of vehicles because we'd run out of gas. We were kind of poor, and so we'd run out of gas a lot. We didn't have money to buy gas, and so we have to siphon gas out of other vehicles. Have you ever done this? No. You often get gas like in your mouth. Right? It's not really your own vehicle or somebody else's vehicle. No, we wouldn't steal the gas. Oh, okay. It's like my uncle actually. He lived right next door, and we'd go down there and we'd ask him, "Can we get some gas out of your old truck?" And he'd go, "Yeah, get some gas." And so this is not really relevant, but if you have a long piece of hose, then you have to provide a greater pressure differential. And if you don't take your mouth out quickly enough, then the gas comes in your mouth. That's kind of gross. Don't recommend it for anybody. Okay, so anyway, this is the Poiseuille equation. let's just finish off with a couple of clicker questions. So I'm just going to ask you, what happens to Q if, for example, your radius goes up? Does Q increase? Does Q decrease? Or does Q remain the same? So if you increase the radius of your pipe, what happens to the flow rate? Does the flow rate increase, does it decrease, or does it stay the same? If I just take my pipe and I make it bigger, what happens to my flow rate? Keeping all things otherwise the same. What happens if I increase the radius? I'm keeping everything else constant. If I increase the radius, what happens to the flow rate Q? Keeping everything else constant. Keeping the change in pressure constant, the length of the pipe, and the viscosity are all the same. What happens to Q? All right, just a few more seconds. I'll stop at 55. Actually, no, we're not going to stop yet. We're not doing so great. All right, so imagine, just forget these things. These things are all constant. All I'm looking at is this R. If I increase this number R, what's going to happen onto this side of the equation in order to keep this equation still correct, in order to say that this is still true? If I increase the radius of the pipe, what happens to Q? Okay, I know that this is hard to answer this in the correct way because it doesn't really seem to make sense. Because if I imagine I make my pipe bigger, what seems like should happen? What would happen to the flow rate? It seems like it should decrease, right? And in fact, in practice, it does. Because you change a lot of other things. When you change the diameter of your pipe, you change, for example, the change in pressure. But I'm saying that the pressure remains the same. So let me ask you again. If everything else remains the same, if I increase the radius of my pipe, I make it bigger, what then happens to my flow rate? According to this, and in order to keep this true. Okay, good. A little bit. I'm going to stop at 218. Okay, A is the right answer. If I just look at it mathematically, don't think about it, because like I said, if you think about making the pipe bigger, then you say, well, the fluid is just gonna slow down, right? But actually, if you keep the same change in pressure, you have a bigger pipe, you have more opportunity to force more fluid through, so you get a larger Q, and that bears out in this fuzzy equation. All right, what happens if I decrease L? So if L, that is the length of the pipe, gets shorter, everything else remains constant, what happens to my flow rate? Does the flow rate increase, decrease, or stay the same? I make my pipe shorter, what happens to my flow rate? Keeping everything else the same. All right, I'm going to stop at 35. I'm going to do one more and I'll let y'all go. My hand back at quizzes. Okay, very good. All right, so if I decrease L, it's in the denominator. That's going to increase Q. All right, and let's say I decrease my pressure differentials. So if, say, delta P goes down, what happens to my flow rate? This should be more intuitive for you. If my pressure differential goes down, I decrease that pressure, what happens to my flow rate? All right, I'm going to stop at, say, 35. Feel free to ask your neighbor. There's a couple of you who don't have the correct answer. I'll stop at 40. Okay. Okay, B is the right answer. If P goes down, if this goes down, that means that the flow rate has to go down as well. All right, let me show you something on the website. If you go to the old quizzes and exams, you might have to refresh your browser. Like, see here, I looked at the web page when it was different, but if I refresh it, there they are right there. Here's our quiz 2. That's one we took last time. I'm going to hand it back. And just as last time, they're not graded like your grades on Moodle, but you can grade it yourself with the correct answers here. You can go and use the quiz. I would write down the correct answers. Now, Olivia, can you hand it over to please? Corey? Here. Olivia? It's what? Wow. Hand that to Jim. Noel? Oh, I think this is Alice. I think that's everybody. You didn't get your quiz, let me know. Have a great holiday, okay? I'll see you next Thursday. All right?